Uh, cool. I hope you guys are able to see my screen. Is it visible? All right. Awesome. So we are good to start. So today we'll be discussing Uber, and there are a lot of things to discuss, just like the previous question that we did about WhatsApp design. So plenty of content to discuss, and plenty of things which may be irrelevant for the today's discussion. So we'll list everything out, that what are we going to discuss in the requirements, what are we not going to discuss in the requirements, and also we will discuss like what essentially you should be aiming to discuss during your system design interview, because you have a limited time during your design round, so you cannot put like 10 functional requirements in 45 minutes round, because you will be hitting X in your foot. You will not be able to if you put 10 requirements in your functional requirements list, and if you're not able to satisfy all those 10 requirements, not able to talk about all those 10 requirements in that 45-minute round, which by the way is never 45 minutes, it's essentially like 35 to 40 minutes. You have to, if you leave the first 5 minutes and the last 5 minutes for introduction and pleasantries kind of discussion. So essentially you just have like 35 minutes for a technical discussion, and you must be utilizing your time very very effectively. So let's start with a few things. So everyone knows Uber, right? It's a ride sharing platform. We everyone has have used it. So this is a very known kind of a application. So let's start gathering with respect to the very first thing that you should be doing when given a problem statement. We should, as we discussed, the very first part is clarifying the functional and the non-functional requirements. And today we'll be discussing few key elements in discussing the functional and non-functional requirements, and then we'll discuss a little bit into capacity estimation as well. That why or why not we should do it. Okay, so let's start with the functional requirements first. So functional requirements, what are we actually aiming for? So I'll be putting in some basic functional requirements that we are looking to achieve with the today's Uber design. So we are the first core requirement that we are looking for is that the user should be able to input his location, his start location, and destination where he wants to go, and see the prices or see the fare basically. So this is the very first thing. When you open your Uber app, you put the input location, it automatically takes from where you are, but you can also put in a custom start location by overriding it and by choosing a custom location. So that's we are just gonna we're not gonna go into that complexity, but it is understood that the GPS of your client device, which is your mobile phone, could be used to determine your start location. And if you want to put a custom location, then you could just enter into that search bar and pick up a custom start location and the destination where you want to head to. And based on that, you should be able to see the fare. So that's the very first thing. And again, Uber shows you the fare for multiple different type of vehicles like Uber X, Uber XL, Uber Go, and blah blah blah. Right now we are not going into that complexity. We are keeping the design simple. Simple in the sense there is already a tons of things to discuss about in this design. How the riders are matched with the drivers on a dynamic basis, how the drivers are able to send their location, their updates continuously. So we'll be discussing majorly on those aspects, and how you should be storing the locations in the database, like what kind of database we should be using, how to effectively search for this for the driver's location, and to match it with the to match a rider with the closest driver in the platform. So I think someone wants to join. Okay. All right. So this is the very first functional requirement that we are starting with. Okay. The second thing that we, along with this, that we want is once a user is able to input his start location, let's just call him a rider. So rider is able to input his start location and a destination and see the fare. The second thing is that once he gets the estimated fare, and let's say if he wants to proceed further and book the ride, so rider should be able to go ahead with booking based on above estimated fare. There's a second thing. So once we have shown him the estimate, and he can just go ahead and book it. So we should be, our system should be able to let him book the ride based on this. Now, when he clicks on book the ride, what really happens at that point? Uber looks for the nearest driver and starts a matching process. So there is a matching algorithm where Uber backend is going to find out the nearest driver to the rider, and that driver should also be able to accept the ride. It should not be like the driver is just forced to accept. So driver, there's a notification that goes to the driver that, hey, this is the incoming ride, do you want to accept it or deny it? Or if he doesn't take any action, then request automatically gets denied from that driver and should go to the second, the next driver in the queue. So we'll discuss about that, but for now we can say that upon the request, the rider is matched with nearest driver, uh, and who accepts the booking. Who accepts the booking? Okay. Uh, so in fact, the who accepts the booking part, I can keep it as a another functional requirement. So the third functional requirement is like the rider should be able to get matched with the nearest driver available. And what happens is when the matching happens, the request goes to the driver that, hey, this is a ride in the queue, do you want to accept it or not? So the next functional requirement is that driver should be able to accept or deny the request. um, and then based on that, and once it happens, then he should be able to, the ride should start. So accept the request and the ride should start uh, to to the destination, like where the drop location, right? So this is essentially the functional requirements that we are aiming for. What we are not aiming for as part of this requirements is like, we'll just mark some of the items as out of scope, or maybe we can discuss it later on if time is there. So the very first thing is about the ratings and reviews. So we are not talking about that user is able to give the ratings to the driver, and driver is also able to give the ratings to the driver. uh, so we are not discussing the ratings and the reviews at part of this. Second, authentication, signups, payments. Authentication, signups, payment are out of scope. So essentially, this design that we are building, because payments, authentication, and sign up is a very generic thing, which we spoke about in the previous as well. So authentication and sign up remains constant for most of the applications. So this doesn't warrant to be discussed as part of Uber design, because this is a standard process. Similarly, the payment part is a standard thing, because whenever you purchase something, you go through the payment gateway. So payments can be discussed as part of a completely different system design, which is only about the payment, like how to build a payment gateway. So we can discuss on that, like how to build PayPal or a standard payment gateway, but not as part of this design. These are the two things. Then we are also not looking at scheduling the rides in advance. So we also have an option, I think, in Uber to schedule the rides in advance, let's say for the next day or upcoming or next few hours. So we're not talking about that, but it should be pretty easy to build. We can touch base upon it. It should not be a very big thing. Then we are not discussing about the different categories of vehicles. Different categories of Uber vehicles, we are not discussing about that, like Uber Black, Uber Go, Uber Luxury, whatever. So those are also out of scope. So this is the functional requirements that we are going to build. These four are our basic functional requirements that we are basically going to build as part of this design. as I said, it's really important to keep the functional requirements just to have 3 to 4 functional requirements, and not more than that in a standard and most of the system design problems. You should not aim to have like 10 functional requirements or six, or even 6 to 7 functional requirements. No, the reason is that when you start doing the design, it takes a lot of time to actually build and to explain and do a deep dive on the functional requirements, and along with the functional requirements some non-functional requirements will also come into the picture. So please make sure that you keep your functional requirements to the core component of it. So Uber, the core part of Uber is the matching part, like how the matching actually happens, how the driver's locations are being continuously updated in the system. And then there comes the multiple challenges with respect to that, like how would you we'll discuss about the non-functional requirements now, so you'll get to know about that. So coming on to the non-functional requirements that we want to build, so a couple of pointers over here is, generally, like in even we used to do that some time back, but generally what people do is they come with a very vague estimates that will have, let's say, billions of users, or this will be the capacity, this will be that. It's okay to discuss that, and for a medium, again, for a senior engineer or a medium level candidate, it's completely fine to discuss all of that and to go into capacity estimations. But for a staff level candidate, please do not do that. The reason is that it burns a lot of time during your interviews, and you do not actually have enough time left to do the deep dives, to discuss on the high level design, to build your system design diagram, and then go deep into that. So you definitely want to save time for it. I'll also keep giving some pointers around it, but for now, just keep that in mind. So coming on to the non-functional requirements, we want to have the non-functional requirements which actually matter for the system that we are going to build. So for the Uber kind of system, first of all, the latency, as we know that when we talk about the non-functional requirements, a lot of things come into play, like latency, consistency, availability, all the cap theorem comes into play, throughput, all these numbers come into play, right? So make sure that when you're talking about these numbers, don't just talk about vague numbers that latency should be minimum. Like, what is the minimum over here? What's the data point? Don't just say that system should be consistent. Like, in what way the system is consistent? Be specific to the problem that we are talking about. So in this particular problem, so either you do not mention that point at all, but if you're mentioning, please mention with some data points. And if you're mentioning those data points, please make sure that those data points could be addressed while you're designing the system. So you should be able to completely satisfy your functional requirements and non-functional requirements, and talk about it, like how this design is accomplishing it. So that's the end goal. Most of the people just put some vague numbers, but when they are actually building the systems, they never even discuss about the non-functional requirements, whether they are getting fulfilled or not. So the very first aspect about the latency part, here the latency is about, with respect to the matching algorithm. So since we are dealing with the actual customer here, like actual rider who is the end customer, so there should be a acceptable latency for him to get a ride matched, because he will not wait indefinitely. Let's say once a user clicks on the second step, so he is able to see the fare estimate, and once he accepts that fare estimate and like goes ahead and tries to book the ride, he should not wait indefinitely. There has to be an acceptable latency within which he should be able to get the ride assigned. So we can say that we can pick a number, and this number can be a configurable number. It doesn't have to be like a hard coded number. So we can say that, let's say, a couple of minutes could be a acceptable latency, that within 2 minutes or within 3 minutes, that the user should be able to see. So this again depends upon the product manager as well, like how they see the system, because they are familiar with the user based patterns. So does a human can actually wait more than a minute for their ride to get booked, or will it be like too much, and they will just simply close the app out of frustration, and they will not So if the ride is not booked within, let's say, 1 minute or 2 minutes, it's futile. It's basically futile to keep them waiting, right? So we can define acceptable latency number. So we can probably say that low latency with ride matching for the end user, for the end rider, or maybe we'll just say the rider, for the rider, such as let's say 1 minute for now. So within a minute, we should be able to book him a ride. If no, the system should fail the request. Like basically we should throw an error that we are unable to book you a ride, and then he can request again if he wants, but he should not be indefinitely waiting for it. So and as I said, this can be a configurable setting, and this again depends upon the engineering. The You can say this kind of requirement actually comes from the product managers, or based on the discussion. It's not in the engineer's hand to decide whether it should be 1 minute, 2 minute, 3 minute. From an engineering side, what we can do is we can make it a configurable setting, so that this configuration could be changed at any given point in time based on the business use case and based on the business demand. So yeah. So low latency here, the latency we are talking about is with respect to the ride matching for the rider who is requesting a ride. The consistency part, consistency, when we talk about consistency can have a lot of meanings, and it can vary a lot depending upon the problem to problem that we are discussing. So I think we have touched base upon consistency in the previous design sessions as well. What does a consistency mean in with respect to with respect to a Twitter design, or a Facebook design, or with respect to a financial banking system design? But with respect to Uber design, what we are actually interested in is that, imagine that, let me give a scenario. Imagine that there's a concert going on, and there are, let's say, 10,000 people attending a concert. So there's a Justin Bieber concert going on in US, and then this concert ends. Let's say the at the end of the concert, people are trying to book a Uber, and they want to go home. Now there are tons of problems that can happen right at this point in time. So the very first problem that can happen is there are a limited pool of drivers available in that vicinity. Let's say, maybe, I don't know, let's say there are tons of 1,000 drivers available, or even there are 10,000 drivers available. Irrespective of that, there's a possibility that the same driver can get multiple requests parallelly. Like, let's say, all these 10,000 people are trying to book their Uber at exactly at the same moment, or within a span of 5 minutes. Once the concert got over, now when they are sending the request, it can possibly happen that the same driver is getting the multiple requests from many different people for the ride. And this is a consistency problem, because a driver should not be parallelly getting more than one request at a given point in time. So he should be able to get only one request at a given time, and he should be able to accept it or deny it or ignore it. If he accepts it, let's say if he accepts it, then it's fine. The ride is matched, and uh, the rider is matched with the driver. And then but if the ride is not matched, if he denies it or if he ignores it, then there should be some, as soon as he denies it, then the next rider request can come to him, but not before that. So consistency basically means that a driver should not be matched with more than one rider at a given moment. So it means that a driver shouldn't be getting more than one request at a time. I hope this part is clear to everyone. Is this part clear? Awesome. Now, next thing is the throughput. What does a throughput means? Throughput is again a generic term, but in general, throughput means like what's the load, how okay, you can think of throughput as how much amount of work done in a given amount of time. So in case of Uber, we can say that like how many requests the system is able to serve in a given amount of time. Now the problem with the throughput is, in our case, there can be two types of situations. One kind of situation is that, let's say, there are some areas where there is not much people are requesting the rides. It's a very quiet kind of place, so very few requests coming. But then there are areas, just like we just took the example of Justin Bieber concert, right? So there can be 10,000 requests or even 100,000 requests, like within a short span of time. Like we call it a burst request, right? So our system should be able to handle burst load during peak hours or festive time. So it can be during a festive time or during a peak hours, any kind of thing. And so example, we can say that 100K request coming in a short amount of time, right? Amount of time. And it can come from a same location as well, like can be incoming from same location. So these are the non-functional requirements basically that we are going to address as part of this. Um, Here we are not okay, so we are not handling a few couple of things over here. We are not talking about here alerting or the logging part, all those things, monitoring, logging, alerting. We are not designing that. Uh, Again, that can be a different problem in itself, which could be which could be designed separately. But right now we are just going to focus on these aspects. So we have and it's good to clarify like what is out of scope, what is in the scope. So this is in the scope that we are going to discuss. And while we are going to build the system, we will also look at like exactly if we are able to satisfy all these functional requirements and non-functional requirements. Okay, now coming on to the capacity estimation. As I said, capacity estimation you can do. You can actually ask the interviewer that, hey, do we want to do a capacity estimation, or we can because most of the people have read this book like Grokking the System Design, right? It talks about doing a capacity estimation, which is which actually doesn't have any value to it, just to be very honest. It just displays your mathematical skills, that if you're able to compute how many billion users are there. But when you're actually building the design, you do not actually use it in any way. There is no practical application of that. You just say that, oh, we are going to put a load balancer and we're going to do a horizontal scaling behind a Kubernetes architecture, so system should be able to scale up. But you're not actually using those numbers anywhere in the design. So time is a very critical factor in these kind of design interviews. So make sure that you have enough time to discuss on the deep dives, to discuss on the ambiguity part, which is expected from a staff engineer. So from a staff role, if you are able to, let's say, even if you are able to discuss the functional requirements, non-functional requirements, and then spend 5 to 6 minutes on doing capacity estimation, it's a waste of time. That you have wasted your 5 minutes. You're not going to get any brownie points for it. And then once you do your high level design, components, APIs, your data model, then you will notice that you are actually towards the end of the you're towards the end of your round, and you have not actually discussed any ambiguities. Like you have not really gone deep dive into some of the components, which is expected from a L5 plus candidate. Okay. But yeah, from a so this is the functional and non-functional requirements we have gathered as of now. The next step that we are going to talk about is the core entities again. So we brought this concept in from the last from the previous design session as well. So just to give a little brief about the core entities. So what do we mean by core entities, and why do we put it over here at this point? So core entities basically define like what are the data. You can map the core entities directly to the tables or the let's say the entities in the database that we will be building, but we are not actually putting the schema here. The reason for that is we may not exactly know at this point like what should be the schema of each table, because a lot of times when you're building a system design, if you have seen this problem before, then perfect, then good. But even if you have not, but if you have not seen this problem before, or even if you have seen this problem but you do not recall exactly each and everything that you studied at that point in time, so you as a candidate will also be is also going to come up with a solution on the go, right? You have not mugged up things, so it also gives you a chance to recollect your thoughts and to just lay out the basic entities that you will be using in the data model. There might be few more entities that you might end up using in the data model that you can clarify while you're building the high level design. So but building a core entity will give you a little bit confidence into building your APIs, like for what entities you are going to build the APIs for. So that's the purpose of putting the core entities here. So here the core entities that I'll be putting is the rider. This is the very first core entity that I'll be having. So rider basically talks about let's say the user who wants to, like anyone or the end user requesting the rights, right? So this is the very first core entity that we'll be building. The second core entity that we will be building is the driver, which is, give me a minute. Um, okay, sorry. So driver, basically what does a driver, so driver, we know that the driver who has registered with our platform and who is accepting the rights. So driver is a second core entity. The third core entity that we want, we can explain it, but the fare is a third core entity that we would be wanting. I'll talk about why do we want fare to be a like data model and not like just a value, a random value. So for now you can imagine like fare represents an estimated fare for a given ride, which basically includes your pickup location, your drop location, and the estimated ET as well. Because when you when a rider inputs the pickup location, the destination, and he asks for a fare, then he also is shown the ETA, right? What's the estimated time of arrival? So this fare could be a part of our ride object as well. Like the next entity that we're going to have is ride, so this fare could be part of a ride itself. But I have kept it separate. The reason is that initially the fare is shown to a user, and at that point in time the ride is not yet initialized. We'll talk about it. So basically the idea is that when the user tries to see the fare between the two places, he's only seeing the fare. Like he's not yet created a ride object. He has not yet clicked on create a ride for me. So at that point in time the ride is a vague idea, but the fare is a solidified idea at that point. And when he clicks on book a ride, what really happens is that this fare is like logged in, and this fare object that got created, or the fare that got created or was shown to the user, gets logged in for that particular ride. So this fare is actually there's a one-to-one mapping between the fare and the ride. So that's the objective. A ride entity, we like it's pretty much evident. A ride basically talks about a given ride, which has the rider ID, the driver ID, the pickup location, the destination, the fare, and bunch of other metadata as well. And then the last one more core entity that we want to have is the location. The reason for that is because the drivers are going to be sending their location updates frequently to us, to the platform. uh, uh, the idea is that the driver application, so the client so we'll be having this application, right? So one application for the rider, one application for the driver. the driver will be continuously sending their location updates to the Uber backend, so that Uber, our system always know where the what's the current location of each and every driver in my system. Because if I don't know the exact location of each and every driver, then I cannot really assign or match the driver with the rider. So if a rider is in a given location, I need to know like what all drivers are in this nearby vicinity. So location is my next core entity. So this basically represents the real time location of so it represents real time location of drivers in the system. So this is the and this basically includes your longitude and latitude. um, okay, so we have basically we have collected all the core entities that we want to build, and we'll be building APIs for them. So the next step is to build the APIs. um, okay, so now we will be building only the essential APIs and not all the APIs. So the very first thing that we talked about in our design is the flow. So user should be able to input his start location and destination and see the fare. So the very first thing is to see the fare. So for that, the user is going to be sending a post request to the system, and we can have a fare endpoint. What it is going to do in this fare, in this request, user can pass in a body in which he can pass in, let's say, the pickup location and the destination. So these can be the destination location. So these can be the two, and again these locations are passed in as a longitude and latitude. So this can be the content of the body of my post request for the fare. um, and what's the response going to be? This is going to return us a fare ID. So the response is basically going to be a fare ID, uh, and which is a unique object representing this fare for a given pickup location and destination. And this is also going to contain like the details, like what's the estimated fare. So this is in the response you'll have the like body of fare ID comma, so you can have fare ID comma, the actual fare, then your pickup location, drop location, etc., and then bunch of other metadata can be part of it. So using this fare ID, the next thing that we discussed was the rider can accept this fare. Basically, he can go ahead and do a booking based on this fare ID, right? So the next thing is that the user should be able to request a ride based on the given fare. So for that, we are going to have a post API again. So whenever you want to create something or send a request for initiate it, so we always have it in a post. The method is post for that. So we're going to be having a post API for it, and we can have a post ride. So this is going to create a new ride. Again, this is going to have a body. In the body, we are going to pass in a fare ID. Now fare ID is going to contain everything. It is going to contain the location, the destination location, the fare price, like the fare of that trip, and ETA and rest of bunch of other things. uh, Please note that one important point to mention, I think I'll mention it after this. So I'll come back to this in a bit. So this is a post API, and this is going to basically return us a ride. So this is simply going to return us a ride ID, right? Once the ride is booked, it is simply going to like return us a ride. um, the next API that we have is, so what happens when the user requests the ride? The request goes to the driver, and the driver, so there's a ride matching algorithm that we have in the backend, and this request is sent to the driver, and now the driver has the responsibility to basically accept it or deny it, right? So we'll come to that. So for that, what we can do is we can have a patch patch command. So the method name is patch for this. And what it can do is it can pass in the ride and the ride ID. Let's say it can pass in the ride ID. So which ride we want to patch, and in the body of this, you can just simply have the two uh, you can have an enum over here which is like either accept it or deny it, right? So this can be like a this can be the patch. uh, can someone tell me the difference between patch versus put, if you guys are aware of the post apis, the rest apis? What's the difference between a patch versus put? The difference between patch versus put is that put replaces the entire thing, like the entire object on the back end. So but patch is used to modify partially that object. So what happens is that in the ride, we'll talk about we have the ride entity. In the ride entity it will be like ride id, and the status of it, whether it is accepted, denied, or it is pending or awaiting the, let's say, awaiting the matching. So if you with the patch you could just update the fields of that entity, and you don't have to replace it fully. But the put is used to replace it fully. So in the put you need to pass in like essentially everything over here, so it will replace the entire object, uh, or create a new one if it doesn't exist. So yeah, good, Anila. That's what it is. um, Cool. Going forward, one more important thing now I want to discuss. Okay, one more API, which is the location update API. So we have the drivers updating their location continuously. So we have a post API where the driver can update their locations continuously. So for that, what is that continuously that we will discuss? So this will be like a periodic, basically periodic update. And the periodicity we can define, it can be a configurable setting. Again, it can be like every few seconds or every couple of seconds, depending upon what's the configuration factor the business demands. So what we can do is we can have a driver location. So this, the URL we are choosing like this is so that it can be extensible in future. So we can have drivers location. It can be a driver's sign up in case new driver wants to sign up, or it could be a driver's payment further if you want to have a payment related to drivers. So drivers, this is the structure of the URL that we are following. So in the location, basically the driver can just simply send his latitude and longitude. So I can just keep latitude and longitude over here as the body. So this can be the body of this. This can be the body of this post request. Now you don't need to go into the detail that whether it's a long, it's an integer, what it is. It's a waste of time, and it's in fact a disrespect to the interviewer. That, I mean, this is a very basic thing that, of course, latitude and longitude are what numericals, right? So you don't need to go into the details whether these are strings or essentially what. You need to save time for the discussions. If you are a mid-level, mid senior engineer, then yeah, if you go into that, it's fine. But staff level candidates, please don't do that. It's not a good idea. So don't spend a lot of time on describing um, the data types. uh, okay, one more question to all of you. Let's see if you guys can think about it. So it's a design problem and it's a security related aspect. So the question is that, um, okay. So one question is that over here, let's say I am sending a post request driver's location. I have not mentioned over here driver ID, right? I could have actually maybe mentioned a driver ID like this and then put a location, right? Do you think this is a good design, or do you think this is a bad design to put a driver ID here? Yes. But why? Yeah, you are right. We can get the ID from the token, but why is it not a good design to put the ID here? Anila, there has to be a strong reason for it. It's a very fundamental thing. And same thing over here in the first request when we have a fare. Imagine that if a user is requesting a ride, why are we putting a fare ID here? Ideally, let's say we could have also directly just put in the fare amount, right? Let's say ki, what's the fare amount? Maybe 200 bucks, right? We could have put in a fare amount over here rather than putting a fare ID. And similarly, when we are requesting a post ride, here we are not putting in the user ID, like for which user we want to put a ride, right? Um, so this is a bad design, and there's a strong fundamental reason behind it. So the very first thing is that these IDs we should be able to get through the token, the authentication token, JWT token, whichever you are using. So the token that a client is sending, it carries its unique identifier along with that. But again, now this becomes like an optional thing, right? Oh, we can get it from there, so it's okay if we don't read it. No, it's not that. It's not a choice. It's by design. The reason for that is if you put in an ID over here, then what can essentially happen is because this is a API being invoked by the client, any client can do a abuse or misuse of this API. They can put in some other driver ID. Like for example, if you expose a driver ID over here, what can potentially happen is a client which is let's say a driver for now, he could put in any other driver ID over here, anyone else's ID over here, and pass in the latitude and longitude. So this will show that, let's say someone is jealous of I'm driving Uber and I'm jealous of my friend who's also driving Uber, and he's making much more than I do. So what I do is I update his latitude and longitude to the Antarctica, that he's currently sitting in Antarctica. So this way he'll not get any rights and he will be basically out of the system. So this is a security threat. This is not a good to have thing. This is a must to have thing. Is this part clear? So Tarun, idea is that a general principle in the system design is that you cannot trust anything coming from the client side. You cannot trust the raw data coming from the client side, basically all these IDs, and you should not trust that. So essentially, even for the fare part, right? Let's say if I had if a user is booking a ride and if we allow him to put a fare directly over here, then he can put in any fare, right? It's a data coming from the client side, so he can just pass in. Maybe he let's say he just wants to make his trip fare pretty cheap. So what he can do is let's say the actual fare was 200, but he will just put in $5 and do the ride. It is possible, right? Our system is going to simply take this and is going to just do a match with the driver, which is wrong. So we cannot really trust a client for that. So for that, what we are doing over here is we are asking him to include the fare ID object, which actually includes the pickup location, the destination, which includes everything, like where he is currently at, where he wants to go, and what's the fare amount, what's the fare amount for this, and what's the ETA. He cannot modify the fare ID, right? Because he does not know what's the other valid fare IDs present in the system. And also, even if he gets to know that, there is no chance that the other fare ID is going to have the same pickup location, destination location, same ETA, and everything. So he cannot really hack into the database, because that's a separate problem in itself. So that's why we are providing, we don't provide him the actual the raw data. So we cannot really trust the data coming from the client side. Does that make sense? And even this latitude and longitude is directly coming from the GPS tracker of his device. So we are not allowing this APIs to be called directly. These APIs should be invoked through your mobile application, and we can prohibit our system, the client side, to be usable only from Android or iOS, for example. And we can maybe BlackBerry as well, if people use BlackBerry. So we can just support couple of platforms. And uh, so basically it means that a person cannot really invoke this API using a postman client, like using your web browser. So a web client cannot be used for it. It has to be invoked from the mobile application. All right. So, and if you and this is a important point to discuss, because if you are not aware about it, like it's an expectation from us, at least from a staff level candidate, to know about all these data points. And if you're not able to talk about it, it shows a red flag on your side that you do not really understand how the systems are built. um, cool. So coming on to the third piece of it. So we have defined in fact, the fourth piece of it. So the first piece is to clarify the requirements. We have clarified and the requirements what we are going to build. Then we have clarified the core entities that we are going to build. Then we have clarified the APIs that we are going to need for these APIs are there to fulfill our functional requirements that we have put into the place. So our first objective is to fulfill all our functional requirements through our system design. That's going to be the very first objective that we want to have. The second objective will be to go into the deep dives and start filling in and start fulfilling our non-functional requirements. And when we go into the deep dives, we definitely want to save at least 30 minutes for the deep dives. So essentially what telling is that please do not spend a lot of time on these aspects. Just keep like talking about it, writing it, and please capture it. So here I'm writing it on the doc. In the interview you can just start capturing it on the whiteboard, like over there, just put in a text box and start capturing it, everything. Um, so um, okay, coming on to the high level design part, right? So onto the high level design, we have we the purpose of this high level design is to fulfill all our functional requirements. We have started with, as I said, four functional requirements, so we will be fulfilling all these functional requirements. Tarun, yes. Yeah. 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 So generally, they will give you a either a hacker rank link. In these days, hacker rank also have a whiteboarding functionality, or they will give you a Whimsical or Excalidraw. So Meta uses Excalidraw. Google just gives you a plain Google sheet as what we are using right now. This is what the Google interviews happen on. No other. This Google Doc has a drawing tool, which we are going to use in a bit. And then Amazon has its own. I forgot. I think Codil. I forgot about it, but Amazon also has. It doesn't really. It doesn't really matter like which platform they are giving in, but the idea is that whatever you're drawing there or whatever you're writing there, it's visible to the interviewer as well. It's like a just like imagine this Google Doc, right? So even if you open the Google Doc, you can watch what I'm writing even without sharing the screen. And they may ask you to share the screen or they may not ask you to share the screen. It depends completely on the interviewer. Most of the times they don't ask you to share the screen, but even if they do, so please be ready for that. Is that part clear? Okay. um, cool. So now what we're going to do is we are going to get into the whiteboarding part, and we're going to draw a bunch of things and talk about it. So I'm going to use, shall I use a better place to draw, or maybe let's just use the Google Doc itself. So I'm going to use a drawing board over here. Okay. So the very first thing is definitely the client we want to have. So this is the rider. Now this rider is basically our mobile app, right? So iOS or Android, whichever he's using, but it has to be either one of them for now. And the generally what happens is that we are building for a one system, and then we can expand on it. So we can say that what we are going to do is we can have a ride sharing a ride service over here. This is going to be our very first service that we are exposing. And imagine, like, right now there is just one instance of it, there is not more than one instance. So all the requests are just going into this write service. Okay. And so the purpose of this write service is going to have bunch of purposes, but we'll start with the very first functional requirement, which is the fare estimation part. So uh, so it is doing a fare estimation as of now, the write service. So this is the first aspect, fare estimation. Okay. Now so this is the very first function requirement. How okay, and what rider is basically asking for, he's putting a post request over here, and this post request is coming to the write service, and the write service is simply uh, getting the fare estimate. How the write service is going to do a fare estimate? Essentially it has to know about the location, right, where the rider is currently at. So rider is going to send both the start location and the destination location in the API. So but to calculate the fare, it has to know about the distance between the both the places, right? And it also needs to know the ETA, like between both the places, depending upon how much traffic is there. Now for that we can use some third party APIs like Google Maps or Apple Maps or any other provider. So we are not going to go into that into those complexities. So we are going to black box it. You can just say that we are getting those requirements from a third party provider, or you can just say that so you I can just put over here, let's say, a third party provider for maps, right? Which will be basically computing the ETA and distance, right? So ETA and the distance between the start location and the end location. So so this is going to be utilized by my ride service, and it can be, as I said, Google Maps or Apple Maps. But there is no point of going into the details because there is a lot to discuss, and this is not even a point of discussion. So you can just abstract the details about it, just mentioning that we're going to use rely on a third party. And then once the third party gives us the ETA or the distance, then we can use our internal algorithms or internal it can be a AI model that we can use to find out the good fare based on the ETA and the distance, and then return the fare. So those things we can black box, and we don't have to go into those specific details. The write service is basically going to be connected to the so it is basically making the API calls over here. Um, okay. So there are two elements to it, right? So one element is you can start with one instance at a point in time, and then you can scale it up. So right now we're just taking a look at the one instance, but even for the one instance, right, so we have a write service right now, which is handling the fare estimation, and then we plan to add a bunch of other services as well, which, let's say, a location service to handle the continuous updates of locations from the driver. And then there could be bunch of other couple of more services as well that we there could be a ride matching service as well that we want to build to match it, but we'll go there one by one. So to implement that, what we can do is, instead of directly connecting them, we could just start with respect to that, the better design would be that we can say, because eventually we have to put it, so we can say that we can start with over here a API gateway. So I'll just put API gateway. So what API gateway is, I hope most of you are familiar with what a API gateway is, but just to give a little recap. So API gateway, the purpose of API gateway is to map the API request to the appropriate microservice in the backend. So right now I have a write service is one of the is like one of the services which is handling, let's say, the fare, the API is related to the fare endpoint. So any API request arriving from the client, it will map to the appropriate microservice. That's the very first functionality of a API gateway. There can be few more functionalities of API gateway, which are these days embedded. All the modules are embedded within the gateway layer itself. So this can be load balancing, this can be rate limiting, and this can be authentication. So all the three other modules like rate limiting, authentication, load balancing can be built in inside the gateway layer itself. So you could just mention that we can have over here auth plus rate limiting, and auth plus rate limiting plus load balancing. So I'll just mention LB. So and the major and the basic purpose of API gateway is to route the request. So it's basically a router for the API request and map it to the appropriate microservice which is handling that request. So that's the main purpose of it. Now once this is done, so what's happening over here is the writer is going to send the request to the API gateway. The API gateway is going to match the request to the appropriate microservice. So let's say it connects to the right service, and it's, I'll just put in the arrows both the ways because it is going to fulfill the request as well. So it is going to return the request to the user, and the user is going to get back the response of its API call that he just made. And it is connected to the third party, and then on the back end, like we can say that we are connected to a connected using a DB. So I'll just make a database over here. So let's say that this is the database that I'm having. um, right now we are keeping it very abstract, like we'll talk about what kind of database it should be and what not. So right now we are just storing the fare, we are just estimating the fare, right? So at this point in time we are just interested in storing the fare. So I'm just gonna put the two-sided arrows because there's like a bidirectional, DB is going to return back the results as well. So um, cool. So the DB at this point in time, this is going to store the fare object. So over here we can put in some text box, and we can say that this actually is going to store the fare object. And now we can talk about the data model of fare, because by now we have got some good amount of idea that what this fare object is going to contain. So first of all, it will have, let's say, a fare ID. Um, this So this is going to contain fare ID. Then we can say that it is going to contain the and by the way, fare ID can is just represented as an ID. It's a fare ID, but inside the data model, the table, it will be simply an ID, which will be a unique identifier of this fare object. Then we can have the user ID, who basically booked basically the rider ID or the user ID. Then the source where he for which this fare is being computed, source and destination. So I'll just mention source and destination, and the price at which this fare is booked, and the estimated ETA that was initially being sent. So what really happens is, once the user makes this call, um, uh, calls the once the user invokes the API request to get the fare, then this fare object is being stored inside the DB, and the fare ID is simply returned back to him. So this is the very first This is the very first part of it. And over here, till now, if you notice, we have let me copy this entire thing because it doesn't let me copy back. So this has fulfilled our very first requirement, that user should be able to send a request to the Uber platform, and he should be able to input the start location, the end location, and he should be able to get a fare estimate. So this is the very first functional requirement that we are fulfilling using this. So here I'm just fulfilling the functional requirements. I'm not going into the non-functional requirements at this point in time. We'll go into that little bit later. So this is the very first functional requirement, and let me just call it as a first functional requirement. Okay, so this first functional requirement has been fulfilled as of now. Now, um, okay. Now the second thing is that so what we have worked through how the calls actually work. So what really happens is the rider is basically inputting the pickup location, the destination location into the application, and he is making a post request uh, to the fare endpoint. So we have a slash fare. We have a fare endpoint to which it is making a request, as in over here, and we are basically sending him all these details about the fare. So this is the very first thing, and also the flow of the system. The second thing is that the rider should be able to request a ride based on this estimated fare. So once we have given this fare to the user, he should be able to book a ride using this fare. So for that, what we're going to do is we're going to come to the second requirement, which is essentially that rider should be able to request a ride based on a fare. So based on the fare. So at this point in time, what really happens is we have this entire thing. So I'm gonna insert another diagram over here, and I'm just gonna copy paste. I can't copy paste it. Sad. Okay, so what really changes at this point in time? The most of the stuff remains same. We have a client over here. So this is the client which is requesting the ride. It doesn't change. Then the next thing is the we have the API gateway. It also remains same. So I'm just gonna put in everything real quick. So this is API gateway. Then the next thing is we have the ride service. So we have a ride service over here. Um, okay, now the ride service is basically handling two things at this point now. So it is doing a fare estimation, and also it is doing a fare estimation, which is the first thing that it was doing. And the second thing it is doing is um, it is also doing the request the ride. So basically or create a ride for the user, right? So create the ride create a ride for the user. So these are the two things now it is handling. So what really changes is that client is making both the calls, like for one is post fare, and then the second is post ride. So all these requests go through the system, okay, go through the API gateway, lands up onto the API service, and so you can just make the arrows appropriately to show that uh, in the database. And then this is connected to the let me just put in little below. So this is connected to the third party system to fetch the ETAs and to fetch the distances. So third party location providers, or third party map providers. Okay, so this is the this is what's being used by this. So we'll just connect it to this. And then we discussed about that we have a database, and in this inside this database we are going to capture, this database is going to store the fare object that we already spoken about. Now we also need to store the ride object, right? The inside our core entities, we had two core entities. One was, we had five core entities. So one was fare, the second was ride. So we saw the ride initially, and we saw the fare initially. Now we're gonna see the ride. Inside the ride we can have again the ID, which is the ride ID. Then we can have the rider ID, who is actually going to the passenger basically. um, then we can have the driver ID, which may not be immediately available. So this, we'll just leave it like empty for the time being. Initially when the ride is created, the driver matching still needs to be done, right, at that point in time. So only the search is happening. So then we can have the fare ID, because a ride will be mapped to a fare on a one-on-one basis. Then we can have a source from where this ride is started, and the destination. Um, these things are already mentioned in the fare ID, so we can probably avoid it. But if, let's say, there is like a denormalization needs to be done, in that case we can, I hope you guys are aware about denormalization of tables, but we can include it if that's a requirement over here. But this can be like discussed later on as well. And then the status of the ride. So status of the ride basically means that whether the ride is in progress, or whether the ride, like the ride matching is in progress, or the ride, or it is on the way, it started, like that. So that could be the status of the ride. So it could be a enum, the status, and we can have pre-decided values inside the inside this. And then there can be a bunch of other metadata related to the ride. So this could be a ride entity, and this could be a data model with respect to the ride entity that we are describing. We already had the fare, so I'm not going to write it. It's going to stay the same as we discussed earlier. So this is going to fulfill our second function requirements. So what happens at this point in time is that the user is going to request the ride, and the request is going to go through the ride service. So the post ride is going to get invoked. It is going to pass through here. It is going to go to the DB, create a ride object for that particular ride request that is incoming, and after that the ride matching is going to start till that. And in the status we could maybe just mention it as requested. So the status could be requested till this point. The driver is not finalized. So because we have just requested for a driver, right? So if it is matched, we could update the status to the matched. And once the passenger sits in the car, then so like once he finally like gives the OTP and starts the ride, then we can just mention over here like on the way, right? Or in drive. So till this point, is the design clear, what we have discussed so far? All right. So going forward, now the next requirement that we had was, we wanted to match the we wanted to match the driver with the we wanted to match the rider with the nearest driver who is available, right? So uh, so for that, bunch of things needs to happen for that thing to basically take place. So first thing is, we need to have the location of all the drivers. Like we need to have continuous updates of the location for each driver. And then we also need a way to match a nearest driver to a particular rider. So for that, what we're going to do is, we're going to have bunch of a couple of services over here. The first thing that we're going to have is the ride matching service. So driver, maybe driver matching or ride matching service. we are keeping it as a separate. And so the purpose of this driver matching service is that it matches a ride with a given driver. So people who are requesting the ride, it matches it with a given driver. And the reason to make it as a separate microservice and not keep it as a part of the same, because first of all, we want to decouple both the things. The drive matching is a complex algorithm. It will be involving like fetching a lot of records from the database and making sure that we are able to match with the nearest driver. Then it will have couple of retries as well, because we will be sending the request to the to, let's say, a queue of drivers. So we'll be sending a request to the very first driver and see if he accepts. If it does not accept, then we'll have to send a request to another driver, and so on. So the idea is that we want to keep it decoupled from the write service. The write service is just going to handle the new request coming from the multiple clients. Let's say all the people who are requesting a ride, it handles that part. And the driver matching service handles the matching criteria, finding out the nearest driver with respect to the ride that is being incoming. And when we talk about the ride matching service, now for now, let's assume that we are having everything as part of the same database. So this one DB is where we are storing everything. So we already stored like bunch of metadata in this already, right? So we have stored a ride entity in this. Then we also stored the fare entity in this. Fare, already talked about the fare object, right? Then we can also look at a driver entity, because there will be a driver entity that we talked about initially. So ride, fare, rider, and driver. So these are the four entities that we talked about, right? So I'm gonna just mention over here the rider can have, let's say, a rider ID, the ID and name and bunch of other metadata. So it's not really, it's futile to go into all of these details like his name, email, age, address, permanent address, blah blah blah. It's futile to go into all of that. And so you can just save time. You can just be like, it will have ID and bunch of other metadata related to the driver. Similarly, for a driver, we will have will have like the driver ID. So we'll have ID, location. Like for example, for now, let's say that the location and everything we are storing with respect to the same inside the same table. We'll take a look at the pros and cons of it, and we'll discuss the trade-offs. So ID, location, and then the metadata related to the driver. So this is these are the two things that we wanna store. So till now, what we have done is we have created a ride service which is estimating the fare, creating a ride on behalf of the users, and storing that ride object, the fare object, the and those information inside the DB. We also have the rider information in the DB, the driver information inside the DB. Now the next thing is the location service, because we want a way to capture the location on a continuous basis from the drivers. So what I'm going to be doing is I'm going to be having a location service. And please note that make it a separate service. Don't mix and match inside the driver matching service, because location service is going to be a completely independent. The purpose of the location service is to monitor continuously the live location of the driver, where he is currently, irrespective of whether he is in a ride or he is not in a ride. So we need to know the exact location of each and every driver on our platform. So what we're going to do is we're going to introduce a new entity first on the client side. So we're going to introduce a driver entity over here. This driver entity is again going to go through the API gateway, and he's going to send us a locate. So he's the purpose of the driver, two things he does. The very first thing is, first he continuously sends his location. He continuously updates his location. So his requests are going to go to the location service, and the location service is going to continuously, let's say for now, the location service is continuously update the database. So we already have this like driver ID, location, and these bunch of stuff, right? So for now, imagine that this location service is going to update the driver's location inside the DB, and driver is going to continuously send his location to us, and this periodicity we can define as maybe 5 seconds or 10 seconds. So any and this can be a configurable number again, so please mention it that this can be a configurable setting. It doesn't have to be a hard coded number. So you can you definitely want to keep it as real time as possible. If you delay your updates too far, then you will not have accurate location of a driver in your system, right? And that will lead to inaccuracy, so you will not be able to match accurately or the closest driver at a given point in time. But if you have too frequent updates, it can put a lot of load on your system. So we will discuss about the load as a deep dive. So right now we are just fulfilling the functional requirements. So this is our third functional requirement that we are talking about. So this fulfills both the parts, that driver is continuously sending his location like periodically every 5 seconds to the system, and we are the location service is handling this location updates and persisting it inside the database. Now the driver matching service, so when a client when a ride let me just put him as a rider. So when a rider creates a ride, he's basically requesting a ride, right? So he's essentially requesting a ride, and he's looking and he is asking to match himself with a driver. So what happens at this point in time is the driver matching service takes the request. So this driver matching service is going to go to the database, and it is going to find out the nearest driver, uh, which is nearest to the rider location, right? So so in the ride request, he has already sent us the start location, right? So we will be finding out all the drivers which are nearest to the start location. uh, how we can do that? We already have stored their location inside the database. So inside the application layer, we will fetch, we'll look into, like, we'll have some logic. Let's, for the time being, let's think about that. We have some algorithm to fetch the nearest drivers at the location, and start sending them the notifications. Okay, so at this point in time, we have basically fulfilled most of the requirements. uh, but there is one more requirement that is left, which is a driver should be able to, the fourth requirement that we had in the design. So if you look at the fourth requirement, I'm not closing it, because if I close it, I won't be able to edit it again. But if you look at the fourth requirement that we had, in that fourth requirement, we had discussed that driver should be able to accept or deny the request, right? So for that to happen, a driver should be getting a notification, right? A driver should be able to get a notification that, hey, this is a request, you can accept it or deny it. So there has to be a notification service that can send the notification in our system. So what we're going to do is we're going to build a notification service over here. What does a notification service do? The notification service uses the platform's notification capabilities. So what are the platform's notification capabilities? If you notice, the client is basically both the rider and driver, they're using either iOS or Android as the platforms, right? These are the mobile devices or mobile infrastructure we are supporting. Both of these infrastructures, or maybe it can be any custom infrastructure, but if we have a support for it, we can support it. But for now, we are supporting Apple and Android. Both of them have a notification support. Like, Apple has something called APN, which is your Apple push notification, and Android, I think, relies on Firebase based notifications. So using the notification service, you can actually send them a notification on their mobile phone, basically notification to the driver to accept or deny the request. Right now we are not talking about the notification to the rider, because that is not a requirement for our design. So for now, what we are talking about is we are going to send a notification to the Let me just put some arrows so that it becomes clear. So this essentially is the notification here, and this is also going to send a notification to the and as I said, this notification can use the platform's internal notification capabilities, that is, or support that is being provided. Like Apple provides your Apple push notification service. So um, similarly, Android also provides the push notification capabilities. So this is using this, the driver can accept it or deny it. But what really happens when a driver accepts it or denies it? We had listed one more API. So if I let me just close it and go back to the APIs that we had built. So if you look at the patch API that we had built, right? What really happens when a driver gets a notification on his mobile phone? So he has to either accept the ride or deny the ride. So whenever he accepts or denies, basically a patch request is being sent from his device to the backend system. This patch request is going to be sent to the ride service. So as soon as a notification pops up on the driver's phone, the driver is going to accept it or deny it, and a patch API request is going to be sent to the ride service. The ride service is going to update the ride object with the, and you have the ride object over here, right? We have the status. So initially the status was requested. The so it will not be requested, it will be changed to something, let's say matched, because a driver has been matched with a rider. So at this point in time, this is the entire workflow. So the driver matching service is going to send a notification to the nearest driver. A driver is going to have the driver has like this popped up thing. The notification, as soon as he clicks on accept or deny, it is going to send a patch request to the ride service, and the ride service is going to update the status of the ride entity into our database, so that our ride entity is going to show the real time you can say the real state, the real time status of the ride object. What really happens if the driver is not matched? If he denies it, then the next driver is being chosen and he will be sent the request. But all of this needs to happen within to make sure that our latency requirement is satisfied, like within the 1 minute thing. But we will talk about that in a bit. So for the time being now, what we have done is we have fulfilled all our functional requirements that we have chosen. The functional requirements that we initially came up with, rider should be able to input his start location and end location and see the fare. Then rider should be able to go ahead with a booking based on the estimated fare. And rider is matched with the nearest driver, which we have done using our driver matching service. And then the driver should be able to accept or deny the request, and the ride should start to drop the for the drop location. So as soon as the rider clicks on, like matched, then the status will get updated. And once the client actually onboards, then we can have, I think there is one more API that we could build, which was to start the ride. So I think the ride start could be done by it could be done by driver. It's usually done by the driver only, but what happens is there is an OTP thing that comes in, and so the rider is first sent an OTP that he needs to share. So that OTP could be sent on his mobile phone as soon as the driver accepts the ride, so as soon as the request is matched. But we didn't talk about that flow because we haven't captured it as a functional requirement for the OTP thing and all. But yeah, those things you can extend if you really want. So at this point in time, we have fulfilled all our functional requirements. Now we are going to go deeper into the non-functional requirements, which basically is fulfilling our latency, consistency, and throughput. And this is going to require like a good deep dive discussion into things. And but before going into there, is this part clear till now what we have discussed? Okay. Uh, okay, coming on to things. Right now, I'm going at a very slow pace because I am explaining much more than what I need to explain, because this is a tutoring session. This is not an interview session. But had I been in an interview session, I would have finished all these aspects like functional requirements, non-functional requirements, core entities, APIs, and even the high-level design in the first 20 minutes, or at least in the first 15 to 20 minutes. I should be able to finish everything till here. For a senior candidate, it's completely fine if you're able to do it in a little longer time, because you don't have to go more deep dive into a lot of non-functional requirements part. That's not the expectation from you. But from a L5 E5 or L6 E6 roles, you should be able to go through this in 15 minutes and have at least 25 to 30 minutes saved for your deep dive and for your non-functional requirements part. Cool. So let's talk about the non-functional requirements part, right? And let's talk about the very few interesting cases that we are going to handle. Now, the very first thing is we need to address like how does the okay, we need to address two things, right? First of all, how efficiently we can match, because the we are if we are talking about the latency part, let's say the latency of a ride matching should be very small. Then to actually achieve this, we are dependent on couple of things. We are actually dependent upon, first of all, how efficient our querying is. So we have to query this location from the database, and we need to find out the nearest location to the driver, right? That's the very first thing. So we need to first of all do a little bit estimation into what's the transactions per second we are receiving, or how many like how many queries we need to do, and what's the size of it, and how do we need to do it efficiently. So and it also depends upon how accurate the driver is with respect to our with respect like how accurately our system is capturing the driver's location in the real time. So we can do some estimations on that. We can assume that, let's say there are 10 million drivers into our system, and it at this point it is actually a good point to do the estimations, because it is helping our system right now. We have built a system, we have built a backbone of the system that we are going to use, and to do a little bit of a capacity estimations from the point of view to explain the design further is a good idea. But don't do it vaguely just for the sake of doing it. So the very first challenge that we have is, let me talk about the challenges part, right, and how we are going to handle it. So challenges slash deep dives. Okay, the very first challenge is the frequent updates of driver location. So this is the very first challenge that we have, that how do we handle the frequent updates of the driver's location. So we have to assume few things like how many drivers are there in the system, how many drivers in the system, and what's the frequency of updates, right? So we can say that, we can assume, and you can assume anything over here, but from the live data of Uber, I think it has more than 10 million drivers onboarded onto the platform currently. And we can say that the frequency of update that we want is that every 5 second, less than 5 second, we want the location updates to be sent from each driver. So if we want to keep track of their location every 5 seconds, we'll look to minimize this number. We can, again, these are all configurations that we have, as I said, and this can, at least the 5 second part is a configuration number that we have, and we can definitely reduce it by changing this configuration. So right now, for the capacity estimation part, we are going ahead with this. So if we take a look at 10 million drivers, each one of them, so let me just keep it 10 million and 5 seconds. So 10 million drivers sending a location update every 5 seconds. It means that there are 50 million requests every uh, every 5 seconds, right? So there are 5 into, mm, yeah, there are like almost, um, every 5 seconds there are 10 million requests. So basically every second, how many requests are being there? 10 million divided by 5, so 2 million requests per second. So this is the so basically 2 million requests our system is getting to update the location overall for the drivers. So this is the load, this is the write, and this is the write load, this is the write throughput, not the throughput, but this is the write load on the system, correct? So we need to first of all choose a database in which we can push these updates, like 2 million updates per second. We need to design a system in such a way that it can support 2 million, 2 million updates per second. And the second thing that we want is how to efficiently query the the latitude and the longitude, right? The lat and long, I'll just mention as lat and long over here. So how to efficiently query the latitude and longitude from the database. Okay. um Okay, now we'll talk about few things over here. So generally, let's say we have a raw table, just a database. We don't have any optimization with respect to the location. So what is going to happen is, in a brute force approach, we are going to query all the records from the database, and then we are going to compare. We are going to compare the nearest location, like we are going to find latitude and longitude from each record in the database, and we're going to compare it with the start location, like which is sent by the user, that where he wants to start from. So we want to find out the nearest driver to the start location of the rider. So when we query this, we have to query all the records, like, so there are, let's say, 6 million, 10 million drivers in the system. So it means that we have to query 10 million records just to find out the nearest one, and then we have to do it repetitively for all the requests that are coming in the system. This is highly inefficient, first of all, to query for all the records in the system. For each request, querying all the records from the database, this is highly inefficient. And second thing, even if we try to use indexing, let's say, even if we try to use some sort of indexing, this is a multi-dimensional data that we are having, because there are two dimensions to it. There's a latitude and there's a longitude as well. And if we even if you know that how the databases work, how the database indexing work, usually database indexing usually work on a concept of b trees. B trees are nothing but a height balanced trees that you can think of, which is having, like, let's say, a log of n time complexity to search. But the problem with that is it is not optimized for multi-dimensional searches. You can optimize it for a single dimensional search, but if you need to find latitude and longitude together, like as a combination, so it is not optimized for a multi-dimensional searches. So given and this first part is the frequency of updates. Since we want to process 2 million requests per second, and this is the right load in the system, so definitely we can think of maybe a NoSQL database to support this much uh, write load onto our system. But even during that, the querying part still remains pretty slow. We'll not be able to query, let's say, the latitude and longitude efficiently from the database. uh, for the first one, we could definitely look at using a NoSQL or even a SQL database, and we can look to have, let's say, multiple read replicas. So if you're thinking about how we can optimize a database queries, if you're using a, let's say, a SQL database, you can have a master slave architecture where you have like all the slaves for the read operations, and you have one master for the write operations. But even here, the number of operations that we are doing is the right operations. So we can think of still optimizing it by doing a sharding, that not all the updates are going to go into a single same shard. We can do a sharding, and then we can optimize it further. But for the read part, to read it efficiently, we can optimize the read part by having multiple read replicas in place. but then the query part still remains a slow, like how to efficiently query just the nearest latitude and longitude. And we don't want to query all the objects from the database. We just want to query, let's say, the top 10 records, which are the nearest ones. So given both of these things, the traditional database is of no choice. Like, the traditional database is not a good design choice for the Uber system design, especially for the location part. For the other things like the ride ID, the fare ID, it is fine. We can go ahead with a SQL, NoSQL database. It is completely fine with that. But with respect to the locations, it is not a good idea to store them in a traditional database. We are going to look at couple of optimizations that Uber actually uses, and before we actually go into what Uber actually uses, we will talk about the few alternatives that you probably would have read if you have looked at the Yelp. I'm sure you would have looked at Yelp design. Some If someone has prepared for system design interviews, I think Lokesh, you were preparing for it earlier, so you might know from Yelp design that we use something called as quad trees data structure. So what does quad tree does? Quadtree basically splits a region into four quadrants. The name, that's what the name is, quadtrees. So if I put some lines over here, let's say, and put a, so what it does is it splits the region into four regions. So there is a four quadrant: the first quadrant, second quadrant, third quadrant, and fourth quadrant. And maybe if I draw this on a whiteboard, it would be much better to explain. So generally, how does a quadtree works is, let's say you have let me draw some lines. So let's say you have a region. Okay, you split the region into four quadrants, and so what really happens is, uh, you start with a number k. Let's say there's a number k, maybe 5, for example, right? So what does it mean is that, let's say there are a bunch of drivers. We split the entire globe into four quadrants initially, and now there are a bunch of drivers. So there's a driver, let's say D1, D2, D2, D3, three drivers are here, and then let's say there are there are like two drivers here, maybe D4, D5, and let's say that uh, there are 10 drivers here, starting from D6 and going all the way up to D15. Okay, so there are 10 drivers here. So what really happens is it recursively keeps splitting the quadrants into bunch of four quadrants each. If the number of k is if the total number of drivers or total number of locations is greater than a given number, is the assigned number. So this k is a configurable setting again. So since we have 10 drivers here, so it will again recursively gonna split this location further into the four quadrants. So it's gonna split it further into four quadrants, and what gonna happen after that is, out of these 15 drivers, some of them is gonna go into the first quadrant, some of them gonna go into the second quadrant, some of them third, some of them into fourth. And if any quadrant size is still more than, let's say, size greater than equal to k, it is going to further recursively split it into set of four and four quadrants each. And what really happens is that these quadrants, like, using these quad trees, it's a tree based structure. So if I draw it like this, in a proper tree format, it actually looks like this. There's a tree, then it has like four childs to it, four children, which are nothing but the four quadrants. So it has four children to it: one, two, three, and four. Okay, so it has four children to it, and this is like the, let's say, the starting node, and then all the children are connected to it. So, and then if a quadrant is more than, let's say, a given size, okay, then that quadrant is further split into four children again. So let's say if this quadrant has more than n number of locations, it is going to be further get split up into size of 4. So this is like the structure of a quad tree usually. um, so this is one way to store. When you're talking about the locations, you can use quad tree kind of a terminology. And for a senior candidate, it's good enough that if you're able to come up with this, it's like it's decent enough. But for a staff level candidate, it's not enough. This is not enough. um, there are few problems with the quad trees and few good points about the quad trees. The good point is that it dynamically splits the locations as per the number of the traffic, or let's say if there are more drivers in a particular region. So imagine that there are 100 drivers in a region, so it's gonna further split that region into smaller chunks, into four set of four more locations, four more quadrants, and then gonna further spread the drivers. But the problem with this quad tree is that the updates are very costly. So there is like so even if these quad trees are stored in a database, generally Postgres is a SQL DB, and it has a quad tree extension that you can use. It's called PostGIS. So it's built for geospatial indexes. So there are databases which has support for the geospatial locations. Postgres has it, and it has its extension. But the one of the problems is that it builds indexes on these locations, right? So that the location search could be easier. So if you have to find the nearest location, you can just start from the root node and keep going into the depth of the tree to find like the nearest location. And then it has, let's say, the k drivers, whatever the number is, then it will return you those drivers in the vicinity location. Or it can, if there are no drivers over there, then it can look at the siblings, and then it can go into the parent, and then can look into the further siblings, and so on. So there can be a complex matching algorithm for that purpose. But one of the disadvantages of having a quad tree is that quad tree only works best for the static locations, the locations that do not change a lot, because it builds indexes on this, and updating an index is a very costly operation in a quad tree. So if there are frequent updates happening, let's say if these locations are continuously being changed, then there's a problem with the structure that quad tree uses. So it is good for the Yelp kind of design, because there the locations are pretty much constant, because nearby places and nearby shops or restaurants, their locations do not change. They are like mostly static. But in case of our Uber design, this is a not a uh, good design. The reason is that drivers keep on changing their location, and quad tree dynamically splits up a location based on the using the quadrants, based on this how many drivers are there in that location. So if, let's say, if a lot of drivers are there at a given concert, but once the concert is over, they move away from that concert, then this quad tree has to be updated significantly. So this is like not a very good let me just write the name over here, what we're discussing: quad trees basics. So these are like couple of trade-offs about the quad trees, and why it's not a good candidate. Like why, what are the issues with the quad trees, right? So even if you do not know the perfect solution, as I have explained a lot of times, if you're able to talk about the problems, the challenges with respect to the current design, that's what they are looking for. That, do you know what you're talking about? Do you know the challenges? Do you know the pros and cons? Do you know the trade-offs? So here we are discussing the trade-offs with the system. So quad trees are supported in the database itself. Like as I said, Postgres has a inbuilt support for it, but the problem is the frequent updates. So quad trees is one option that like we could use. But yeah, this can not be like a good thing. And second thing, also one more thing I would like to discuss is to address the this 2 million requests per second. What we could do, essentially one way of addressing this is that we could so here right now we have addressed the very first part about the efficiently querying the database. So we have discussed that one of the approaches could be a quad trees, but it's not a very highly efficient approach, and we will be looking into a second approach after this. But before going over there, we can talk about the first part as well, right? The 1 minute. approaches to handle above. So one is the quad tree based structure that I discussed about, and quad trees could be implemented, as I said, implemented using native support from databases. Example, Postgres uh, plugin, plugin support for it. I can just You can just mention Postgres support for it, right? So it's called PostGIS. Okay, so this is one way, but and to address the first part, which is the frequent update, so one thing that we can do to address the frequent support with respect to, we could, instead of doing like a updates every 5 seconds, what we could do is we could batch, um, like we could still do the updates every 5 seconds or maybe 10 seconds, but we could batch the request. So instead of each driver sending a request, sending an update request every 5 seconds, we could do a batch processing. So instead of writing every single record in a database, we could do a batch. Let's say we can have a batch of 100,000 records. So instead of 2 million requests per second, it will be 2 million divided by 100,000, right? So that we will be writing a batch of records at a given moment in the database. Instead of writing one single record every time, we could batch it up. um, but the problem with the batching is that it will delay the writes. So let's say, so batching is one possible solution, but the challenges, the trade-offs with that is, it will definitely, the good point is it will definitely remove this huge load onto the database, and it will, instead of 2 million requests, we can, like, boil it down to 2 million divided by 100k, which can be like 20k request per second, something like that. But the trade-off with that is, since we are batching, it means that we have to wait for that entire batch to complete, and it will not be accurately able to capture every driver's location. Basically, that we will have some latency with respect to capturing a driver's exact location. So if a driver has sent the update at t0, but since we are waiting for the batch to complete, so we will be, let's say, able to send this update at t0 plus delta. So this delta is like a latency, and during that time, the location of the driver could have changed, right? So and this delta is also going to be problematic when, let's say, within this delta time, a rider has requested a ride. Now, since we don't have the updated location of the driver, so the results will not be very accurate for the rider who is requesting the ride. So there are like a lot of trade-offs with respect to using a batch method to resolve this frequent updates. To handle both of them, what we're going to do is, instead of using the second approach that we're going to take, and to resolve both of them, or to address both of them, is going to be, instead of using a database to have these locations persisted, what we could do is, we could use a in-memory cache or a in-memory data store where we can persist all these locations. And in-memory reads and in-memory writes are pretty fast. So what we can do is, we can use, now definitely we cannot use one server in memory, right? Because that will be inefficient and will not be able to scale up. So we cannot use, like, the driver matching service will be, let's say, there will be multiple instances of this driver matching service. So we cannot put it on a single instance. So we definitely want a distributed in memory cache, which can be in form of a redis cluster. So we can use a Redis cluster. And also, the good part is, Redis provides support for geospatial indexes. You can search for Redis geohashing. So there is a concept called Redis geohashing, which also is used by Uber. So Uber uses geohashing. It may not be directly using from Redis, but similar idea according to that. So Redis also stores it in a similar format as a quad tree, but Redis does not rely upon this k parameter. What it does is it uniformly takes the world map, like the entire map, and it uniformly partitions it into the, let's say, all the recursively partitions it until it finds the minute, let's say whatever is the minute granular level that it can partition up to. And using that, it builds, like it stores those locations with respect to that geospatial indexes, geospatial locations into the Redis. We call this concept as a geohashing with respect to the Redis. And Redis offers like geo search command or geo radius by. So geo search and geo radius basically tells you that within this radius I want to find out the, let's say, the drivers, or I want to find out the entities within this particular radius of a given start point. So you can get it in a pretty optimized way. So basically to so that addresses our second problem, which is efficiently querying the latitude and longitude from the database. So we can talk about over here is that we will be using in memory store, distributed um, distributed in memory store uh, to capture geospatial data, and to capture the geospatial data. And so Redis is going to be useful for this. We're going to use Redis geo hashing. And as I said, Redis provides multiple commands, like you could add a new location using geo add. You can use geo search. These are inbuilt capabilities. You don't need to know about all of this, but you can just, if you know about it, it's good. For a staff level candidate, if you are able to talk about all of this, it's a very very positive sign. For a senior candidate, it's not expected. You're not expect Even if you have just discussed till the quadries is good enough for you. But from a staff level candidate, you're expected to talk about what are the drawbacks with the quadries, and then what are the various ways of handling it. You may not It's completely okay if you don't remember the exact APIs, but you should be able to talk about what are the alternative ways. Then the second part is with respect to handling the frequent updates. So Redis can support up to 1 million. Redis can support up to like 1 million queries per second, or writes per second. So it can easily support up to 200k to 1 million, or even beyond that. It has a very good, um, it has a very, like the write, the number of transactions per second or the writes per second, I think it can go beyond 1 million easily. I don't know the actual numbers, but it can support in the order of millions of writes per second. So you can talk about this thing. And second thing, but still this is a huge number, right? 2 million requests per 2 million transactions per second. It's a huge number. Can we do something about it? This can be like a deep dive question, that can we do something about it? We'll talk about that as well. But let me first ask few basic questions. uh, do you see any challenges with respect to using a Redis? So we talked about that we should not be using a database. Database is not a good design. We talked about why database cannot be a good design, because efficiently querying part is like it sucks. Database doesn't have any way to efficiently query for the two dimensions. And then we talked about the geospatial data. You could use quad trees, but then we discussed about the challenges with the quad trees. It does not support multiple update operations. It's not very efficient with that. So then we talked about using the Redis. Okay, so let's say that the driver is in a low profile location, right? He's not in he's not in a New York City where there's a lot of requests coming. Let's say he is in a very suburban area. He's not in a downtown. So what really happens at that point is, we know that there are not a lot of riders who will be requesting the rides in that location. Like there's a very less density of riders in that area. who are looking, there are not much people looking for a ride in that area. So we can slow down the frequency of updates. So rather than 5 seconds, we can say that from the, and this logic can again be inbuilt in the application in the client side. It doesn't have to be in a server side. So basically the challenge that we are trying to solve, essentially, is that, um, like, how can we reduce the frequency of updates from, or maybe how can we reduce the frequency of updates, frequency of location update. Yes, so that it doesn't overload our system, basically. Because the challenge is that the more the updates are there, it's going to overburden our system, right? Our system is already like handling these 2 million requests per second. And imagine that if we keep onboarding more and more drivers into the platform, then this number will only gonna go up. This number is not gonna go down, because we wanna onboard as many drivers as we can, and this numbers keeps increasing, right? So definitely we want some, it is overloading the system unnecessarily. So we want to bring it down as effectively as possible. So we can say that, and yeah, Tarun, you perfectly pointed out that we only want the high quality updates. We don't want just any update from, like the so someone who is static, their updates not going to make a lot of sense. Someone who is in a suburban area, who is not, let's say there are not a lot of riders in that vicinity, it's not gonna, we don't really care about updates every 5 seconds. Even if we send updates every 30 seconds or every 1 minute, now this frequency could be tuned based on which location he's part of. This can be like a logic that we can have an algorithm to decide. Like we can probably segregate regions into, let's say, tier 1 regions, tier 2 regions, tier 3 regions, or what categories we could define. And based on the category, we could adjust the frequency of updates from the client side. So this is definitely going to bring down the number of calls, that number of transactions or queries that driver is sending us. So that is like a one challenge, right, that we have solved. So these are the deep dives that we are talking about right now, right? We have already talked about the functional requirements, how we are going to solve it. Now we are basically talking about the non-functional requirements part. So if I just go back and again talk about this, so here we are talking about the latency part, right? The latency part, that low rider should be matched within a 1 minute thing. So so as I said, we'll look into how to achieve this latency, how to achieve the consistency part, and how to achieve the throughput part, right? So um, these are the main things that we are looking at. So the very first thing was that if we are able to, the low latency we are able to achieve, the reason being that what was the factor contributing to the latency part? The major factor was to actually query in the database the nearest drivers possible, right? So if we look at a design, the initial design that we had, when a rider has requested for a ride, the driver matching service looked into the database. It found out like what are the nearest drivers. To find out the nearest drivers, it had to scan this entire db list, this entire db, all the locations basically, and then do a matching algorithm to find out the nearest location with respect to the nearest location with respect to the rider, and then give it back. So this was the time taking thing, right? We optimized it using our, first we talked about the application of a quad tree, which is basically a geospatial data structure which handles the locations part in a good way, better than the traditional database. So rather than just storing the latitude and longitude in the database, if you use a quad tree, it's much better. But then quad doesn't support the dynamic, it's not very efficient for the dynamic updates. So for that purpose, we used a distributed in-memory store to capture the geospatial data. and and as I said, it has a geo Redis uses a geo hashing capabilities, so it can store your it can provide the search, like geo. It has these APIs, geo search, geo add to add a new location, to basically add a new location into the database, and to efficiently search uh, a location. And you can provide over here the radius and other things, like give me the nearest locations within this particular radius. So you could basically, and this is pretty fast. So using the in memory store, we are able to bring down our latency to, like, this should work within a, like, in a order of a milliseconds or so. So what we are going to do is, the idea is that to solve this challenges, we'll be sending the request to the driver. So we'll be finding out the nearest drivers from our Redis. So instead of this DB, we'll be using a Redis cluster to store the location, and driver matching service and location service are going to talk to that Redis in memory DB, or you can just call it as an in-memory database. So that is pretty efficient. That should work in an order of milliseconds. But what's going to happen is the driver matching service is going to also use a matching algorithm, right? Like, for example, it might internally use that who is the if the driver has a better rating, or if he like multiple criteria that we can also add into our algorithm. So it's a search and ranking algorithm basically. If you look at, if you have seen the search and ranking models, so this could be using a search and ranking model, basically. So it will first search inside the database, which is our Redis cluster, and then it will rank those drivers, like which driver is the first to be sent the request to. So then what's going to happen is, it is going to pick the one driver, and it is going to send a request to that driver, and it is going to wait for some time, like, because the notification is going to pop up on the driver mobile, and driver will have some those let's say we can say that 10 seconds driver has. So it will take at least 10 seconds. We're going to wait for some time before driver can actually accept it. If a driver denies the request, or if we don't accept the request, then we're gonna do the same process. Like, we probably would have cached the results, let's say the list of 10 nearest drivers, and then we're gonna try with a second driver, right? And to do the same thing, and then the third driver to do the same thing. So this is like, this is the flow, and then we are only going to wait for 1 minute, because that's our latency constraint. So main latency would not be from the system side, because we are using in-memory data stored for the querying part, and we are querying on the geospatial indexes, like geospatial data structures. So it will be pretty fast in terms of querying. It wouldn't take like, it should be a order of milliseconds. But the major time that will be taken is the driver has to accept or deny the request. If he doesn't accept the request, then we have to look for the another driver and do the same thing. And then we can have a the system can cancel the request if, let's say, this 1 minute has already been passed. So the ride the driver matching service can basically can just simply return to the ride service that, hey, unable to fulfill the request, and it could be sent back, right? That could be one option. So this way we could basically fulfill our latency requirements. Is this part clear regarding the latency requirements, how we are fulfill we basically address all the bottlenecks in the system, uh, what all bottlenecks could be there in the system with respect to the querying part, and with respect to the volume of the updates coming into the system. Um, so I hope this part should be clear regarding the latency. Okay, now let's talk about the bigger challenge over here. Can you think of the second problem that we had is that one a driver should not be matched with more than one rider at a given moment in time. Now this is a very complex problem to handle. This is like a concurrency uh, part, and this problem applies to your ticket booking system as well. So let's talk about this problem. What really happens? So what happens at this point is, let's say, now assume that there are multiple riders who are trying to book a cab, right? So imagine again, I would like to go back to that uh, example where there's a concert going on, and let's say thousands of people have just come out of the concert, and all of them are trying to book a cab. So what happens at that point is that the request flows into the ride service. All people, like, this ride service is independent service, right? So it is able to handle all the request, and for each one of the rides, there's a driver matching service. Driver matching service is going to take the requests in, so all the requests will be like accepted, and for each of the request, driver matching service is going to find a driver. Now the problem is that since all the people are in the same location, it means that all the drivers who are also in the same location, they are a match to, like, they are the potential drivers for the same set of riders, right? Any one of those drivers could be picked up. And in fact, the search and ranking algorithm that we are choosing, it is going to search the drivers, and it is going to sort them based on whoever is nearest. Now imagine that there were only five drivers in the nearest location, right? And one of them was the nearest, second one was like second nearest, third one was like little far away, fourth one was more far away, and fifth one was the farthest. Now for all the 1,000 people, the same driver will pop up, right? The driver matching service is gonna choose the same driver for, because he's the nearest one, right? How So he's going to basically pick the same driver for all the requests, and it is going to send a notification. Now imagine that it is going to send a notification for all those 1,000 requests, and the driver phone, the mobile, that the application of the driver is just ringing like continuously, like 1,000 times, like brr, brr, it is just buzzing, and he's like, he will go mad looking at all those notifications, right? And whose ride it will accept. So the concept is that what we want to build is, we only want we only want to send just one request to a driver at any given moment, until he has till the time he has not accepted it or denied it. Any further request should not be sent to the driver. Is this requirement clear, what we want to accomplish? And what do you guys think how we can solve it? It's a very generic problem. It's even the same problem that goes into the ticket booking, where multiple people are trying to book the same seat in the aeroplane, in the plane or movie hall, anywhere. So it's a generic problem. How do you think we can solve it? Hmm. um no, but so let's say we use a queue, right? uh, so what, let's say there are five drivers, right? We have, or two drivers, we have driver one and driver two, right? And so what are we saying here? That let's say there are five, let's say there are two riders and two drivers, right? Two riders are requesting a ride and two drivers are there in the vicinity, for example. Now what really happens that two of them requested a ride, and these two drivers are matched by the matching service, but one of them is picked up because he's the topmost driver based on the ranking algorithm, for example, right? So the same driver will be sent two requests, correct? So it means that even if we use a queue, that's a waste of time, because what really happens is, first the second request will unnecessarily land up inside the queue of the first driver, when in fact second driver was actually completely free, right? uh, and it may also happen that the first driver rejects the first request, but to reject the first request, he yeah, Tarun, just 1 second. So to even reject the first request, the first driver took 10 seconds, let's say he did not reject it, he just took 10, he just ignored it, and then the second request will also just land in his queue, and so 20 seconds will get wasted for the second request to stay inside the queue, and then the same thing will be tried on the second driver then, right? And the second driver will not, again problem will happen because second driver will again get two requests one by one. So let's say if he accepts the first request in the first place, then it means that there was no available driver at all, right? Like the driver was not there, and we just let's say there was a third driver available but he was not the in the ranking model, then the amount of time now like can you see this problem piling up? Like this is uh, the the amount of time, the amount of latency this design will add for the entire to the entire system will be huge, and 1 minute will easily get passed once you hop on to, let's say, 10 drivers, your or maybe 4 to 5 drivers, you basically had the available driver, but still you were not able to meet the demand, and 1 minute would be passed by that time and you would have to cancel the request. um, so that would not, yeah, matlab that would be a trade-off. That's a good, that handles one thing good. Like there are, it handles one thing good is that a driver will not receive more than one ping or one trigger at a moment, right? That's what it solves, but it doesn't solve the latency part. And so yeah, any other, yeah, Tarun, you were saying something, yeah. Amazing. That's what I was looking for. So the solution here is using the logs. But now we'll talk about the logs part. So yeah, that's a good thinking, Tarun, and we are going to use logs over here. And even the solution that you gave is very good solution. Like what we can do is we can insert we can like change the state of that driver to let's say uh, that he is already having a request, something like that, right? We can change the status of that. That could be like he's currently engaged, or he's currently, there's an outstanding request for that driver, right? So this way the system will know that this driver is already busy right now, so system will not even attempt to send a request to the driver. Basically the new request will not even go to him, it will go to a second driver in the from the search and ranking model that we had. Um, now uh, e- yes, Manasvi. Long polling, so long polling is basically a concept used for client to server communication, right? Mostly um, like when a client wants to interact with a server, so we discussed about it, like we have multiple ways of communicating. One is like a client ask, so we talked about single unidirectional communication, we talked about bidirectional communication using WebSockets. We talked about like a polling, a long polling is a way where client does not periodically polls a server to ask for an information. Rather, he can initiate a long-lived connection which has some expiry, a TTL to it. And if a server has a data, it will respond back to it, right? If a server does not have data, and let's say that that TTL expires, then a client has to initiate that request again, which is a long polling request again. So long polling over here, how are you thinking that long? Like I didn't get it. Mm-hmm. Yeah. Right. Okay. Okay. See, the concept here is for any kind of concurrency control where we have like multiple concurrent people requesting the same resource. There's a resource crunch. Uh, this is a resource crunch problem, right? We have a one driver and so many, like we have few drivers. We have few resources who are looking to get mapped to the set of drivers, right? Set of riders. So this is a resource mapping problem, and definitely there's a resource crunch over here, as we can see. So what we can do over here is we can use a locking mechanism. So what really happens is, uh, how do we implement locks? Locks is nothing but, in a traditional form, you could like on a low level design, you could implement an application level lock using semaphores, mutexes. On a database side, you can still implement a lock by just simply inserting a record in a database, so that when other and let's say putting some value to that record. Let's say for example, I have changed the status of a driver to outstanding request, like this driver has an outstanding request to it to itself. Now if other, let's say if a driver matching service is getting another matching request from the, so let's say there are five people who are trying to book a ride. So as soon as the first request, the driver matching, so what it will do is driver matching service is going to contact, pick a driver for one of the requests. And as soon as it sends a notification, it is, before sending a notification, it is first going to check that whether this driver has any outstanding request or not. So one of the solutions can be that it can simply go and check, it can go and see the value of this lock. Now where this field is going to reside, that's a major design challenge, right? One option can be that we can put this variable in the memory itself, in the rights, let's say in the memory of the driver matching service, for example, right? This very, we can just put a in memory key value store, and we can just say that the driver id, the id of the driver, and the status that it is currently has outstanding request. Do you, this can be one solution, right? If I just put in the memory about this value, this can be one solution, isn't it? Can you guys think of the pros and cons of this solution? So if I just put inside the memory of my driver matching service itself, that this driver id is currently, so that the next request it is getting, it can just simply check whether this driver actually has an outstanding request or not. So, can you think of some pros and cons with respect to this? Is it a good design or not? It doesn't depend on the request. It's just a driver ID to its status mapping, right? Just a map. It's a hash map, basically. Like, what's this for this driver ID? What's the, it does it has any outstanding request? And let's say once the request is fulfilled, let's say once the driver accepts the ride, then we can change this value to maybe in ride, for example, right? Or something else, so that this driver is no longer available to match. And I think that need not even be there, because when the driver, these drivers will be picked, their state we are already maintaining, right, in the database, whether it is. So one option is like we could have a in memory locks, which is a application level locking. So it means that the driver matching service application is responsible to maintain the locks, but it's not a good design. The problem with that is that, first of all, it's a distributed architecture, so there are multiple instances of driver matching services running. It's not just one instance of it running. So it means that even if one instance sets the value of this parameter in the memory, in its memory, its value has to get synchronized with the multiple services, right? Multiple instances of this driver matching service, which itself is a complex operation. Like it will take some time, there will be some latency associated to it, and now we are talking about 10 million drivers. So we have to synchronize the, and let's say we have 100 instances of this driver matching service. All the instances have to be knowing they have to synchronize. And the problem with that is, if there is a synchronization might take some time, right? There can be some latency with respect to the synchronization itself. So there can be some inconsistencies where the two instances, let's say two different instances, are trying to lock the same driver object, but they are trying to lock their inside their own individual memories, right? So instance one is trying to store this driver id and its state in its memory, and the instance 2 is also trying to do the same thing. Now since the state synchronization has, let's say it might happen in a couple of seconds, or maybe depending upon what synchronization algorithm we are using. So there could be a inconsistent state that when one instance doesn't see the state of the second instance, right? And this way there can be potential race conditions, like the same driver is logged by two different for two different requests. It can potentially happen, and in that case, or more than two also, and the same driver is getting and the whole purpose is defeated, that one driver should not get multiple requests, so the whole purpose will get defeated. Is this point clear, like why the application level locking is not a good idea? Okay. And the second thing is that we also need to have some timeouts, right? Because if we are setting this lock, we know that there has to be some TTL with respect to it, right? It cannot just stay like driver is currently, let's say, driver is the request is outstanding for the driver. It cannot be indefinite. There has to be some TTL, like there has to be some expiry related to this field. So we can say that after 10 seconds this request is going to this lock is going to get deleted, should get deleted. Now the problem with the application level locking is that if we use the application logic, we need to maintain the timer as well, right? That hey, after 10 seconds we need to change this flag back to, we need to clear this flag after 10 seconds. So either the request will be accepted at that time. If the request is accepted, then the database itself will get modified. So inside the database the state will get changed, so that the driver matching service will not even give will not even have this driver in the potential list of available drivers, because he's no longer available, he's already in transit. Or he can deny the request, in that case he should be available, right? So this lock should get cleared after some point in time at least, and there should be a TTL, like time to live. So if we are manually managing these TTLs, it's not a good design, because manually managing TTLs means we have to keep a timer on an application level, and this timer has to clear off this object, has to delete this entry from the map. So this is a bad design from these two reasons. The second way to handle this whole thing is, we could use a database only flag. So rather than storing this flag inside the memory, inside the memory of each application instance, what we could do is we could actually just store this flag inside the database instance. Like for example, in the driver, let me scroll back. In the driver entity, where have we driven it? Not really. So let's say driver has ID, location, and the status, right? What's the status of this? So let's say if the status is uh, currently pending request or outstanding request, for example. Now we say that we are relying on the database to do this for us. Now it solves one problem. It solves what problem it solves? It solves a problem that we don't have a concern of concurrency part, like multiple uh, like how to synchronize the state, because it is at one common place now, and all the instances of my application can just simply, or multiple requests can just simply read the there's a single source of truth now, which is the database. So it's not a problem for that reason. But do you see any problems or any challenges with respect to storing this flag inside the database. Not really. So databases support let's say they support transactions. So if you look at the databases, they have the transactions. So as part of a transaction, only one of them can really acquire the lock and update it. So even if two, um, let's say two different requests are trying to set this value of a flag, then the problem, only one of them will be able to do it, because the transaction level locking you can acquire. And so this will resolve this is not a problem. Let's say no, we are using, let's say, database is little slower than in memory, yes, but let's say not too slow. We have a good uh, databases are not that slow. So not you're slightly right, but not really. So basically, problem is that with respect to the read replicas, so the concept is that the write operation happens only on the master, right? And yes, that can be one issue. Like, so basically, what you're talking about is whether all of them are able to see the same value or not. So it may possibly happen that the master is updated, but now when the second let's say second request is coming, so it's first going to check whether this value is already there, the lock is already existing. So it can check from a read replica, and at that point the read replica might not have been updated. So it might try to update the value in the master. And but we can have some mechanisms, right, in the master, that hey, this value is there, then just return false or don't update it, right? So those, yeah, we can solve those challenges, like, yeah, but they can be there is more trivial fact rather than that, which leads to this as a bad design. What about others, Anila, Manaswi? What do you guys think? Okay, right. Mm, okay, but let me ask one basic question. I talked about TTL, right? Time to live. How will this TTL going to be decided? Let's say when if I store it in the database, is, let's say, for example, who is going to manage this TTL? Like, how will this record should get deleted from the database? Who's going to take care of it? Yes, the problem is that we are still relying on application service itself, because someone has to actually keep a track of the timer, isn't it? The database, uh, we'll talk about if database provides this functionality. DynamoDB does provide this functionality, but it is not very reliable. So if you go and check the DynamoDB architecture, DynamoDB gives you that flexibility that you can have a TTL columns, but it does not really delete the column once a TTL does. It has, like, it can get deleted immediately, or it can get deleted after 10 minutes or 15 minutes or 1 hour after that, there's no guarantee. That's what I got to know when I read about the DynamoDB architecture. But the problem in our case is that if we just use database, we need to keep a track of the timer in our application layer, right? Hey, like some application is layer instance, it means that driver matching service instance has to keep a track of whoever acquired the lock. It has to keep a track, keep a timer, and then go and make those updates. This is going to have like this is going to have a problem. So imagine that if that instance of the driver matching service got restarted for some reason, right? Or it got crashed, then it acquired the lock in the DB, but it failed, like it literally failed to update the lock, to remove it once the TTL was over. And first of all, since it was only having it in the like it was calculating the timer in the memory, so that's a bad design. So if the service crashes, like if this instance crashes, another instance will definitely come up. But the instance that got crashed, it was storing that timer, like it was running that timer in the memory, and it had to relinquish that lock. But since it died down and it restarted, now that lock is acquired indefinitely. It means that this driver will be blocked indefinitely, and he will not be able to accept any rights in future until this lock is relinquished. Does that make sense? Yeah. So how does a driver gets logged? Let's say the request is coming, the driver matching. Let's say there are multiple instances of this driver matching service deployed, right? So one of the instances is going to get the request, and it is going to first go and check in the DB if this driver is logged or not. Like if the value, if the status of the driver, so in the driver entity, if the status of this driver is outstanding request or not, right? So, and if it is not outstanding request, then it is going to mark the request as outstanding, like acquire the do a transaction and mark the status as in transit, or maybe outstanding request, and then send the notification to the driver, right? That hey, you have a pending request, accept it or deny it. And then internally it will put a timer, like hey, after 10 seconds, just like whatever happens, just delete this, irrespective of that, just delete this lock, so after 10 seconds. uh, so problem is, if this instance got restarted or crashed, then it may happen that all the locks that this acquired, all the set of locks on the drivers, all those drivers would stay indefinitely locked. There is no way that those drivers will get unlocked. So that's a bad design, because we are not we have solved one problem, to keep the lock um, to basically keep the lock outside of the matching service. So that's a good thing, but then still the timer is with the matching service itself. So that's a problem with that design. We are going to look at, so essentially what is expected during the interview is that you are able to talk about these data points, right? A system design is like a storytelling, like as I'm telling you a story that okay, we can try this, but I can see these are the trade-offs. So if this dies down, then there could be a potential issue that the driver can get logged indefinitely. So that's a little optimization onto the previous thing, but not the best thing. So I think the better thing, so you should convey it like that, so that it feels like a story, and it feels also like you understand each and every bit of the system that you are explaining, right? um, the last thing that we're going to discuss, which is going to handle it gracefully, is using a distributed lock. Distributed locks are the things that are used wherever the concurrency control we need to we need. So distributed lock, how does it work? Distributed locks with TTL is what we're going to store. So let me just write this concept as distributed locks with TTL. What's the concept of a distributed lock? So distributed lock is essentially, first of all, it means that the TTL is going to be maintained with the distributed service which is maintaining this log. It is not it is going to be decoupled from the um, it is going to be decoupled from the driver matching service. That's the very first thing. So essentially, we can use an in-memory store like Redis. Again, Redis is very famously used for the distributed logs. And you can keep a how can you distribute can you use Redis for that? Just to give an example, you can just simply set a value inside the key value store, let's say driver ID, and you can say that outstanding request, okay, for example. Now, even if there are multiple requests incoming for that driver, so what really happens is you are using a in-memory data store. It is pretty quick, like rapidly fast. You whichever instance sends the request to the wants like gets access to that first, it is able to acquire a lock. It means it is able to set a value inside this Redis map, and it's a distributed, so it is the the replication part is handled by Redis cluster itself, so you don't have to worry about that. And also what you can do while you are setting this driver ID, let's say I set this driver ID, I can also assign a TTL to it. So these two things I can pass in, I can put inside my Redis cluster. So uh, this TTL, this is already available inside the Redis. So what really happens is this key value. So I put driver ID comma, let's say in transit, for example, right? Or maybe outstanding request. um, and we don't even need to put outstanding request. It can just simply be a hash map, and we know that if there is a value, if there's a driver ID present over there, then or there is a set, like Redis also gives you a sorted sets as well. But here we don't really need a sorted set, but we could just need a set. So you could just insert a driver ID and you could put a TTL with that request. So what really happens is you can put a TTL with that record. So this record will automatically get deleted after the TTL is over. You don't have to do anything. Redis will automatically take care of deleting it. Your application layer does not have to continuously go and check it whether the timer has passed or elapsed or not. And so using this, we don't have to really take care of deleting the request, or and once the TTL is over, it means the driver ID will be removed from the Redis, and the and this driver is available to be sent the request again. So this expiration automatically is supported by Redis, and this driver and this ride matching service can start sending the new request to this driver again. So is this part clear? Like, how did we handle this entire thing? Yeah. Yep. Absolutely. Um, so yeah, that's true. And again, the main problem is about now how much you can rely on the Redis. That's another piece. So if you have to discuss, like, let's say trade-offs, so you can discuss about potential drawbacks or challenges with the solution. Is that we need to ensure, like, how much we can rely the system's reliance on the availability part, right? So if there are any failures that happen with the Redis cluster, we should be able to recover from those failures and make sure that the information written in the Redis cluster are not lost. So if the information was like driver ID and the TTL, and if something happens to that cluster, then this information should not get lost. So this is already supported by Redis because it achieves a good amount of replication factor as well, and I think that is configurable. So so yeah, and in the worst case, what could happen? The worst case, what could happen is that even if the cluster is lost, then it means that all the locks are like relinquished immediately, right? Like all the locks are immediately taken off. So basically, those drivers are not locked. So only in the worst case it will impact your system only for 10 seconds. It means that for the next 10 seconds the driver, same driver, can get multiple requests. You know, like he was having an outstanding request and he did not really accepted it. But if he accepted it, then in its database entity, his like the state will be changed to in transit, right? And that could be a persistent in the database. But before that, let's say if he has not accepted the request, he's still in the outstanding. In the worst case, if Redis cluster fails, all those logs will get deleted, for example. Then what, in the worst case, what would happen is a driver can get multiple requests in the meantime. So which is like fine for the 10 seconds, this failure is acceptable, right? In the even in the worst case, if your system has to recover from the failure, that could happen. But it is still better than indefinitely locking a driver and never sending him the request. Okay, so we have basically discussed about all the potential scenarios, what could happen during this design. There are few more things that we wanted to talk about. One is like how to make sure that, let's say if there's a peak period happening. Let me ask this question to um, it's like too late, but one scenario is that imagine a peak hour. It's a New Year's Eve or a Christmas Eve or a Justin Bieber concert, and everyone is booking a ride from the same place, or maybe from a one particular area. Or suddenly the entire uh, world wants to travel, wants to just go and book the cab, and there's a burst of traffic. So what could really happen at that point of time is that the ride service may not be able to handle all the requests. Like it's a scalable service. It means that the new instances will get instantiated. But the problem can be, even to instantiate those instances, it takes some time. Like, but imagine that there are 100,000 requests coming in 5 seconds. Then you cannot really instantiate those 1,000 replicas of new replicas of write service immediately at within 5 seconds. So like the auto scalability is there, but auto scalability is not quick enough to support the burst load. So how do you think, like, first of all, this is a challenge. Like, this is a challenge that I talked about. The auto scaling cannot really auto scaling does gracefully, but it does not cannot really handle this burst load suddenly. um, and then your service might be down for that period, which is not a good idea, right? So how do you think you can handle it if these burst loads have to be supported? This can be another potential I'm just giving you, throwing you all the questions that interviewers can ask you. And by the way, these questions are for the staff level candidates. So if you're really aspiring for meta E6 E5 roles, please make sure that you work on these kind of questions. Just drawing a couple of boxes, as I said, these boxes and everything that we draw, you should be able to get it done within 15-20 minutes max. And the rest of the time you should be able to save to do these deep dives, because these deep dives are going to is going to get you inside these companies. Only otherwise interviewer is not going to mark you through to these rounds. Um, uh, no, it may be a different scenario. Let me give a different scenario. Let's say that this is not a burst load in a single location. It's a burst load across. Let's say it's a New Year's Eve. Suddenly, it's just New Year, or it's a Corona happened, and now everyone wants to go to their home. Everyone is just going from here to there for some reason, and suddenly the whole country is traveling, whole city is traveling right now. Something happened and now people from different places are traveling. So there's a suddenly there's a burst load in your entire application throughout, not just in a certain region, but across all the regions. But it happened in a very quick succession of seconds, like within, let's say, within 5 minutes, and your write service is not able to auto scale that rapidly, as rapidly your number of requests are incoming. One option definitely is, which is definitely a good point you made. Rather than to fail our write service, what we can do is we can use a rate limiting over here, like in the API gateway. We discussed that API gateway can have these three four components, like it can have a authentication layer, load balancing layer, rate limiting layer. So if it has a rate limiting module in between inbuilt, then it can, and it knows that this is the maximum capacity, these are the number of queries per second, or number of requests per minute my write service can accept. Or in that case it can simply reject the additional request. So that, but that would cause a availability issue, right? Like users are, you're denying the service to your users. It's definitely better than crashing your entire application. Yes, it's a good point, Lokesh. uh, so definitely an improvement over that, but still you are causing unavailability to your end users, right? And it may potentially happen that a lot of those users might get mapped if the request, if your write service was able to handle the load somehow, maybe with some latency, rather than satisfying that 1 minute thing. Let's say add a little bit more latency and match a driver to them. Let's say the drivers are there in the system, because even when the load is increasing, then even the drivers got active, you onboarded more drivers onto the system. And or maybe drivers were already there, but they were on the leave, and suddenly they also came back because they know that this is a peak season, everyone will be going for the ride. So let us work 24 into 7, like let us work more overtime, so we'll be driving them. Yeah, that's a reasonable solution, yes. So we can put a queue, we can have a, basically, queue is, we are taking all the requests, we're not dropping anything, but we are sending them to the right service is gonna pull the pull the request from the queue, depending upon how much it can fulfill in a how many requests per minute per second it can take. And then all those users who requested for a ride, like they can wait. And I think people can wait, like even on a New Year Eve, even I had tried to book an Uber and it would make me wait for 5 minutes, and I don't have an option to do any option, I would just simply wait, and it would just notify me once I am matched with a driver, right? That pop-up will happen. So that's completely okay. So that's a one potential solution, yes. And it will help us that, to we can so that will give sufficient breathing time to the right service to horizontally scale as well. And not so basically we are unifying the load on the right service rather than having a burst load on it and make it fail completely. We are unifying the load by putting a queue so that it can consume at its own pace, and it can, and let's say it can horizontally scale as well. It will get some breathing time to get horizontally scaled. And once the sufficient instances are there, then it can simply empty the queue, like it can consume from at a faster pace. So yeah. And even if, let's say, due to some reason the write service goes down for some reason, the request will be still in the queue. Yeah, yeah, Tarun. Right. Yeah, but that's not part of the requirements that we're building, like the ratings and reviews. So yeah, I get it. What you're saying is the queue part, the priority queues, right? And definitely with the queue, there are some challenges also that we should talk about. I think one of the challenges with the queue is that queue is a first in first out model, right? So first request in, that should be the first request out. But let's say that there are some users in the queue who are having the kind of like destination they want to go to. No driver wants to go there. Like let's say you want to go from, I don't know, like some shady place. A driver don't want to go there, so their requests are not getting fulfilled, right? But the problem is that they stay, since they are in the first in the queue, until their request gets fulfilled they will not be taken out of the queue, and this will block the rest of the other request as well. So that can be a challenge with the queues. And yeah, that can be there, but TTL how will be handling in the queue. So TTL part we were handling in the application logic, and yeah, but let's say the TTL, we are saying that we will give you a right. We are like, but yeah, TTL, waiting till TTL can be a like they will again send the request, and again it will come into the queue and block the other request. um, so so basically we can use, to address that, we could use a priority queue where we could decide a priority based on some, and this priority can be dynamic, can be dynamically allocated priority. So based on like the as you said, the factors like ratings and which location he's going. And we can how do I say it, we can have a priority queue first of all, and then we can shard this queue based on the region. Like there could be some region based partitioning. Basically we can partition this queue based on the regions as well, so that even if some regions, so that some users do not block the entire traffic, even if those users are not getting fulfilled, at least other regions are getting fulfilled, and there should be some way to prioritize these requests. Even if that user sent the request first, but if its priority is less based on customer rating, etc., etc., so those requests can be pushed back into the queue. And so yeah. But yeah, at least the challenge part, even if we are not able to solve the challenge, but if we're able to define the challenge, that's a good piece. So we don't always have to solve the challenges, because some of these problems are like industry wide difficult problems to solve.